All right, hey Math 146 students. We're going to be looking at section 6.5 today on the Central Limit Theorem. Which frequently I'll abbreviate as CLT. So if you're looking in the notes and you see somewhere where I've written down CLT, most likely that's what it's referring to as Central Limit Theorem. And we had a little bit of an introduction to the Central Limit Theorem in 6.4 when we looked at the sampling distributions, and we talked about how, first of all, the larger the number of samples that we included in the sampling distribution, the more normal shaped the distribution became in terms of its being unimodal and symmetric. But also we talked about kind of 30 being this magic number. And if you take a look in your textbook, there is a theorem in there in section 6.5 called the Central Limit Theorem. And basically, here is what it says. If we know that x, and remember x is the raw data values, so raw data, if the raw data values are approximately normally distributed, or if we have a large enough sample size, in this case if n is greater than or equal to 30, then x bar follows a normal distribution, with the mean of the x bar distribution being equal to the population mean from the population of x values, and the standard deviation of the x bar distribution being equal to the standard deviation of all of the x values in the population divided by the square root of the sample size. Okay, so here's what that says. So the mean, the center of the x bar distribution, is identical to the mean of the x distribution. They're actually exactly the same. But the standard deviation of the x bar distribution is actually smaller than the standard deviation of the x distribution. And indeed, as the sample size increases, the standard deviation of the x bar distribution decreases. And we were seeing that when we watched the computer simulation. The larger the sample size, the less spread out the data became, the more peaked around the mean, and the less overall spread there was. Okay? So that's part of what this is saying. What this is going to allow us to do is to compute probabilities associated with x bar, associated with averages, rather than just computing probabilities associated with x values, with raw data, like we've been doing in 6.1 through 6.3. Really important to note is that somewhere in each of these problems, in order to compute probabilities associated with x bar, somewhere in the problem it either has to say that the original raw data is approximately normally distributed, or it could say something about being mound-shaped and symmetric, or being bell-shaped. It's got to either use that verbiage, or we have to have a sample size of at least 30. Only one of the two of those criteria has to apply in order to be able to compute probabilities associated with x bar. It's not an and, it's an or. Okay. So here's what we would do. To compute probabilities regarding x bar, first, we want to check to make sure the problem says either something about normally distributed or we have a sample size of greater than or equal to 30. If it doesn't say anything about either of those two things, we actually can't proceed with computing the probability. Okay? Or rather, we could, in terms of numerically, we can compute it, but it wouldn't make any sense because we wouldn't be assured that the data are following a normal distribution anyway. We might be using a distribution with completely the wrong shape. Okay, so it's got to say one of these two things. Then we convert from x bar to z using the following formula. It's a variant on our regular z-score formula. So z is equal to x bar minus the mean of the x bar distribution divided by the standard deviation of the x bar distribution. And according to our theorem up here, the mean of the x bar distribution is simply mu, and the standard deviation of the x bar distribution is sigma over root n. Okay, so when we're converting to z-scores, but we want to convert x bars into z, rather than using our normal z-score formula, x minus mu over sigma, we use x bar minus mu over sigma divided by the square root of n. Okay, so our z-score formula changes a little bit. This value in the denominator here is referred to as the standard error of the distribution. So there are a few problems where the book will ask you to calculate the standard error, so it's just talking about this part here. And then once we have converted from a probability statement involving x bar to a probability statement involving z, just like we usually do, then we'll use normal CDF to calculate the probability for the given z-scores. Okay. So that's our three-step process for computing probabilities regarding x bar. I do want you to put this little caveat in your notes. Note, this process is only used to find probabilities for x bar. Okay? To find probabilities for x, we still need to use z is equal to x minus mu over sigma. Okay, so really you're going to want to read these problems very, very carefully. There are some, if I remember correctly, in section 6.5 where it asks you to find probabilities for x. And so if that's all you're asked for, you're going to use the old formula that we were talking about in 6.1 through 6.3 and do those just like normal. If it asks you for a probability associated with x bar, that's when we're going to use this new three-step process. Okay. So you'll really want to read these carefully. The difference between the x and the x bar is huge. It makes a very large computational difference. So what I want us to take a look at as an example is from page 305, number 16. And 305, number 16, is looking at some data regarding white blood cells. It says, let x be a random variable that represents white blood cell count per cubic milliliter of whole blood. Assume that x has a distribution that's approximately normal. So there we see that wording that we need to see in order to carry on with the rest of this. It has a mean of 7,500. And it has an estimated standard deviation of 1,750. And those were in white blood cell count per cubic milliliter. Okay, so white blood cells per cubic millimeter. Okay. Then it says a test result of less than 3,500 is an indication of leukopenia. This indicates bone marrow depression that may be the result of a viral infection. So one of the things that we can do by testing people's white blood cell count is to see if they've got some kind of a virus or some kind of an infection. So in part A, we're asked what is the probability that on a single test, X is less than 3,500? So if I want to write this as a probability statement symbolically, I want probability of X being strictly less than 3,500. And this is one of those examples that I was telling you about where in 6.5 it'll throw in some of these that are just going to be what we've been doing in 6.1 through 6.3. We'll convert this X value to a z-score using our z is equal to x minus mu over sigma, and that is where we will start. So if I take my X value of 3,500, subtract my mean of 7,500, and divide by my standard deviation of 1750, then I can get my z-score. And pardon me really quickly while I punch this in. 3,500 minus 7,500 divided by 1750. And we get about negative 2.29 for our z-score here, following the book's convention of rounding to 2 decimal places. So asking for the probability that a single test, X, is less than 3,500 is the same thing as asking for the probability that Z is less than negative 2.29. And if we're thinking about our normal curve, that looks again something roughly like this. Here's our 0, negative 1, negative 2, negative 3. Negative 2.29 is going to be, you know, here somewhere. And being less than that, we'll be shading on the left. That's going to be a pretty small probability. So we're expecting something small when we do our normal CDF. And here when we do our normal CDF, again we'll put in our leftmost endpoint, which since we're going all the way to the left, we'll put our negative 100 placeholder in there, all the way up to negative 2.29. And when we run that through, 2.29, close out the parenthesis, we get a value of about 0.01 or about 1%, which the book keeps 4 decimal places, so they keep 0.0110. Okay, but there's our tiny probability that we were expecting. So on a single test, the likelihood that somebody has a white blood cell count that's less than 3,500 purely by chance is a very low probability. It's only about 1% of the time that that would happen. So normally then, if you had a single test that was less than 3,500, we would say, okay, there's probably something going on. You probably have some kind of infection. The interesting thing about that, however, is for really important tests, really high stakes tests, you don't ever take just one blood test. Typically, doctors will do repeated tests and take an average of those tests over time, simply because you could have a weird day where you just, not necessarily with your white blood cell count, but depending on what it is that's being tested, you can have a really odd day. Like let's say we were looking at that glucose data from the other day. If you had, oh, you know, you're supposed to go in after a 12-hour fast. Well, let's say that the last thing that you ate was something really sugary and you didn't remember that you ate it within 12 hours ago. So you go in, you have your fasting glucose drawn, and it's way higher than it would normally be. Well, they could diagnose you with diabetes, or they could say, you know what, we're going to do a follow-up test later to see what your glucose level looks like 3 months from now and average those two together. And that's actually going to be closer to your true blood glucose level rather than a single test. So that's really what we start looking at in Part B. Part B says, suppose the doctor uses an average X bar of 2 tests taken in this case a week apart. And what can we say about the probability distribution of x bar? So we can say that x bar will be normally distributed because the original data were approximately normal. If it hadn't said that up here, notice we don't have a large enough sample size to assume a normal distribution for x bar. We would need them, if it hadn't said approximately normal up here, we would need this poor person to take at least 30 blood tests so that we could average them and know that they were going to have a normal shape. Okay, so thankfully we know that the data, the original data, is approximately normal, so we can get away with whatever sample size we happen to have. So they only have to take 2 tests. And so we would repeat this again, only this time we're looking for what's the probability that x bar is less than 3,500. Now we're going to need to use our new z-score formula, the one that's x bar minus mu divided by sigma over root n. We need to take that sample size into account. It's not just a sample size of 1 anymore, it's a sample size of 2. Okay. So here we're going to start by taking our x bar value, which was 3,500, subtracting our 7,500, dividing by sigma, which is 1,750, over root 2, since in this case our sample size is 2. Okay, so if I take 3,500 minus 7,500, and then divide by sigma, which is 1,750, over the square root of 2, we get about, I believe, negative 3.23. Okay, so that's what we get for our z-score this time. So the probability that x bar is less than 3,500 is the same as the probability that z is less than negative 3.23. Whoops, 23. And notice we're going even further out into the tail this time. So we had 0, negative 1, negative 2, negative 3. We're actually out beyond negative 3. We're expecting this to be an even smaller probability than we got last time. So it should come in at less than 1%, since that's what we got last time, was a 1% probability. So if we put in our normal CDF of negative 100 and then negative 3.23 and run that through the calculator, we do indeed get a much smaller value. It says it's 6.19 times 10 to the negative 4, which is a decimal point, 3 zeros, a 6, a 1, and a 9. And the book will keep these 4 places. So this is, largely speaking, really unlikely. It is incredibly unlikely that a healthy person with no infection would have an average of these 2 tests coming in at less than 3,500. That would be really unusual, and so normally we would say that that was indicative that something was going on. They have some kind of infection going on. Okay. Then they have us in part C repeat the same process, only this time we look at tests, 3 tests taken a week apart, and so we just change the sample size here to 3. It gets even less likely. Okay, there the probability drops down to be less than 0.0002. It's really, really tiny. So as this sample size increases, the probability keeps decreasing, keeps getting smaller. Okay. So then in part D, it asks us in the textbook to do an interpretation. And it says, compare your answers to parts A, B, and C. How did the probabilities change as n increased? So the probabilities decreased as n increased. Then it says, if a person had X bar less than 3,500 based on 3 tests, what conclusion would you draw as a nurse? So here what we're saying is it would be incredibly rare and by incredibly rare, we're meaning approximately 0% if we rounded to 2 decimal places. So incredibly rare for a healthy person to have 3 white blood cell tests that average less than 3,500. So our conclusion, if it's unusual for a healthy person to have 3 white blood cell tests that average less than 3,500 by chance, then our only choice is to conclude that the person's not healthy, that they have some kind of infection. So the person most likely has an infection. Okay. And this is just one example of what you'll see in section 6.5. You have a number of problems to practice on the homework. I will have my iPad with me while I am gone at the conference, but basically that computational piece, converting from X bar to Z and then doing normal CDF, that's primarily what section 6.5 is about. If you do have any questions, feel free to shoot me an email and I will answer them as soon as I can. Thanks for watching.